Hi, afternoon everyone. We'll be starting class in 1 to 2 minutes time. To answer the question in the chat, some of the problems that you're going to be encountering throughout the entire lectures are going to end up using those approaches. So you'll get practice on them regardless. And when you get to your group assignments in particular, you might get some practice problems regarding those. In the meantime, if you are looking for practice problems regarding those approaches, I would suggest that you look for common recursion problems in particular, and you want to look for the problems and solutions, see about how they go about finding the solution and seeing the approach that they take in solving these problems and how they go about formulating the solutions themselves. Alright, good afternoon everyone, and today's lecture is going to be based on the topic of space and time complexity, which is going to be our longest topic for this course in particular. The reason being is that space and time complexity, when it comes to the performance of your programs, is actually quite important, especially for determining how much memory your program uses, how fast your program can operate within a given set time. And we won't be watching how do we analyze this with respect to the code written to determine the performance of a program in regards to space and time complexity in particular. One thing that we will note though is that the focus in this lecture is going to be a little bit more on time complexity than space complexity, but we will discuss space complexity as well for us to see, okay, how can we actually formulate the equations that represent space complexity of an entire program by watching how much memory you can physically take. Alright, so let's get started. So the notation that we're going to be using for space and time complexity in particular is going to be what we refer to as the big O notation. And for any programming interview, it is important that you know how to use this notation to represent your space and time complexity of any given example code that may be presented to you during any sort of programming interview. It's also quite important to know that if you wrote a more efficient algorithm versus a less efficient algorithm back to your code itself. So let's start with an analogy before we actually get into a physical problem with regards to the code. So if we do have a file on a hard drive and we need to send this to a friend across the country as fast as possible, which one of the two ways is going to be faster? Now, the first thing you might say, well, okay, it's more convenient to do electronic transfer via the internet. And that's true if the file is small, but if the file is extremely large, then what would be the most efficient way to transfer this? What about if there's a high urgency on getting the file, and what if you have to manage a cost of transferring the file as well? So these questions come into play when you start thinking about your complexity analysis, as well as if your code is going to be more efficient or less efficient. So you need to keep in mind these sort of questions that's going to be asked when you're going to be faced with space and time complexity. So the runtime for time complexity is what we refer to as big O time. And mapping this to each one of these methods here, if we say electronic transfer here is O of S, where S is the size of the file, this means that the file size increases, the time also increases linearly. However, if you're physically delivering the file, meaning that if you put the file on some portable hard drive or a flash drive, and then you jump in your car, you go across the country, and you reach your friend's house and you give it to him for him to offload, the time that's going to take is going to be O of 1, where 1 basically represents a constant, meaning that even though if the file increases or decreases in size, it will not take any longer for this file to reach to your friend, because it's going to take the same time to load on the hard drive, and then jump in your car with the hard drive and go to your friend and then reach by him and offload it on the hard drive and so forth. It's just going to be the same time no matter what. Now, if we graph this, O of 1 here being a constant is going to be a horizontal line here, because it's going to take the same time no matter what for your file transfer. And O of S here is going to be linear with a constant gradient. And one thing to note here is that no matter what this gradient here is going to be for O of S, at some point it's always going to exceed O of 1. And that exceed point is where you know, okay, O of S is no longer efficient and you should be really doing an O of 1 algorithm instead, or O of 1 method instead, to get your file across in the most effective way possible. Now, besides O of S and O of 1 that we just now saw here, there are many more runtimes that do exist, and typically we use the n notation for these runtimes. They might get like log of n log of n squared, 2 of n. In some cases you might get square root of n. You can get really weird mathematical notations for your order of n, and it's possible to have any one of those mathematical notations to describe your time complexity order of n for an algorithm. And there's no fixed list regarding this. It can be any mathematical notation that you can think of. Now, the mistake a lot of people make is that they think, okay, because the notation is always with respect to n, that means all notations need to be with respect to n when it comes to space and time complexity. But that's wrong. It's possible to have multiple variables in your runtime because those variables behave differently from one another. So, for instance, like our example here, if your time to terminate the fence is going to be w meters high and w meters wide and h meters high, we can map that length and breadth here with respect to the time, and we can say that's going to be order of w of h. And then if we add another layer on top of that, meaning that you need p layers of paint, meaning how many times you need to repeat this, then your complexity becomes O of WHP, where these variables here are multiplying with each other because they compound with one another accordingly. Now, there are different notations that you may encounter regards to the big O notation. There's big O, which is going to describe the upper bound of the time. There's big omega, which describes the lower bound of the time. There's big theta, which basically describes the two above that, and is referred to as a tight bound. And you may see all these three here, and in textbooks and whatnot, but for all purposes and for interview purposes, we're always going to be using big O here. That's going to be giving us the tightest description of the runtime. So we don't care about capital omega, we don't care about big theta, and so forth. We're going to be using big O notation to make things simple, and we're going to be using it to get the tight bound on the runtime. We want to see why this is important, because the upper bound and the lower bound of the runtimes you want to see throughout this lecture, it's not going to be very important whatsoever. Those are going to be some extremely rare cases when you do happen to get the tight bound around time, which is also referred to as your average time, is going to be the case where that's going to happen the most regarding for when your algorithm or your code runs. Alright, so before I continue, are there any particular questions regarding the analogy or the notations that we just now saw here? Big O basically describes the average time for which your algorithm is expected to run for most of your cases, regardless. And you're going to basically see that throughout the entire lecture, when we start with the code examples, why this big O is going to be important regardless. There's also some cases where you end up using the big O notation to describe how much space your algorithm takes, how much memory you are going to allocate as well. But the importance is to see how well is your program optimized, because you want to see if your program can perform as fast as possible, as well as use the least amount of memory possible, instead of it like taking extremely long to execute and using too much memory. So this notation is a very important notation to see in how effectively you can write your algorithm or your code to have the best possible performance in regards to time and space. Right, doesn't seem like we have any further questions regarding this, so let's move on with the lecture. We're going to use a practical example here before we actually go about describing these, and this is going to be defined as the best, worst, and expected cases. So if we have something that we refer to as a quicksort algorithm, which we're going to be actually learning about in 2 weeks' time, the general gist of this is that it's going to pick a random element in the array, and it's going to use that as a pivot. And anything that is less than the pivot, it's going to put that in before that in the array, and everything that is greater than the pivot, it's going to put that after that in the array. So just to illustrate what this looks like, let's say we had 2, 3, 10, -1, 6, and 5 here. And let's say we choose 5 here as our pivot. So anything that's less than 5, we're going to put to the left of it, and everything that's greater than 5, we're going to go to put it on the right. So we can say, okay, 5 is here. So we start with 2. 2 less than 5, so we'll say, okay, yes, that's 2. I'm just going to put 5 here. Then we check 3, that's less than 5, yes. We check 10. 10 is going to be greater than that, so we put 10 here. -1, less than that, yep. Then 6, that's greater. And we basically finish at that point. And then we choose another value and we keep on the pivots and so forth. But that's basically the gist of how the quicksort algorithm runs until it sorts out all the values in its proper order. What we're going to look at in particular is what's going to be our best, worst, and expected cases for this sorting, as it keeps on repeating until we get the entire array here sorted from the least value to the most value here in particular. So the best case regarding this algorithm is that we only have to do this once, meaning that we get extremely lucky and we find the middle point on our first pivot when we select this, and everything less than that pivot is going to be in order, and everything under that's greater than is also going to be in order as well. So we only do this once, and we refer to this order here as O of n, where n is the number of items in the array. So we only traverse through all the items, which is n items, and we define this as O of n in the best case. The worst case is that we don't traverse the array once, and each time when we choose the pivot, it's always going to be the biggest element in the array. And we will never get that nice division of elements across the pivot. It's just going to be like all elements are going to be skewed onto one side of the array, because that's going to be the biggest element in the array, and that biggest element is just going to be on the right hand side all the time. So in that case, the runtime is going to be O of n squared, because we're going to be doing n times to sort each one of those, multiplied by n times for the repetitions of the sorting. So we get O of n squared as a result. Now, best case and worst case are extremely rare, and we don't really watch these in particular because they're not very important. The expected case, which is what's going to happen most of the time, is what we refer to as a runtime of O of n log of n. And I'm not going to explain why it's O n of log of n at this point. I'm going to come back to this. I want to see if you guys can actually formulate why it's going to be. or n of log of n. And it was a mere worked example, yes, but what's going to be important here is not getting towards this final answer, but your approach as to how you formulated the results here. And that's what's going to carry the most marks regarding your assignments and your quizzes in particular. So just to repeat what I just said, best case time complexity, it's not very useful. That's going to rarely actually happen, like once in a blue moon or something like that. And in most cases, your worst and expected cases are going to be the same. Sometimes they're going to be different. When they are different, you actually do have to specify what they're going to be. But most of the time, you can just have the expected case, which is going to be the average case, and you'll be pretty much okay with that regardless. So we're going to be paying attention to this in particular while we start with code examples to see how do we formulate this expected case. Now, space complexity is also important because that determines how much memory your program uses. So what we observed there before was time complexity, seeing how fast your program was going to run. But with space complexity, we still use the same O notation, but the n here is no longer capital, it's just going to be column. So we use common variables instead to represent your space in particular as well. Unless otherwise stated that, okay, we're going to be like, this is time complexity, and we just happen to use common variables, that's perfectly fine as well. So, in our general example here, if we create an array of size n, because it's n variables that needs to be stored in the array, that's going to be O of n space. If it's a two-dimensional variable of size n by n, that means it's going to be O of n squared space. Now, similarly, that how we just now saw here, that you can have multiple variables representing your order. If our array here was size n by m, the space complexity is going to be O of n m, because n and m are distinct in nature and there's no relationship between the two of them. So once there's no relationship defining these variables, they are going to be treated as independent of one another, and you have to list them out accordingly in your order or your big O notations here. If they are related, you can reduce them down into one single variable, and you can just get away with like O of n and so on. But so long as there's no relationship between the two of them that you can prove, they have to be independent of one another, and they will be stated in the order notation as follows. Now, space complexity plays a very important part when you start writing recursive functions, because as we saw in last week's lectures, recursive functions, whereas they do take up less lines of code, they use more space or more memory in particular because of the repeated function code. So let's observe why this is going to be important here by watching a simple recursion function here for the sum, where we have return n plus sum n minus 1. Now, this code here will take O of n time regardless, but let's see why it's going to take O of n space in particular. So each function call here is going to add a level to the stack. And the stack here is basically, you can think of this being your memory allocation on your computer for the program. So if we said n here started at 4, we'll go sum of 4, then because it's n plus sum of n minus 1, this here is going to be sum of 3. Then it repeats, so we go sum of 2, sum of 1, sum of 0. Each one of these instances here means that you need to have your n allocation here for each one, and it's going to be repeated for each one of those function calls. So for sum of 4, we have its own instance here of insum. Sum of 3, because of the recursion function, we then have its own instance where n is equal to 3, and so forth for 2, 1, and 0. So each one of those function calls there has its own memory allocation because of recursion. And that's why it ends up taking O of n space accordingly, because we only have to deal with one variable here being n. So this will be n equals 4, n equals 3, n equals 2, n equals 1, n equals 0. And because n goes from 4 to 0, that takes up O of n space accordingly. There are some cases where you may have n cores, but that doesn't mean you will end up taking n space or O of n space. And this is particularly true for iterative functions. So if we have k of sum here, meaning that it just returns a plus b, and if we call this function here in an iterative function, meaning a for loop, yes, this here, we see the for loop goes from 0 to n. There will be O of n calls to this pay of sum function that we see here. But these calls don't exist all the time on your memory stack, because the function here is iterative in nature, not recursive. So each function call here, once it does find its results and it stores it in sum here, it means that the function is finished executing and it doesn't rely on any other previous or future values, and it can just exit here accordingly until the next iteration in the for loop. So because the calls do not exist simultaneously on your call stack or memory stack, you only need O of one space for this function call each time it is called, until it goes out of scope of the for loop here. So yes, there will be O(n) calls to pay of sum, but the space required for each instance when pay of sum is called here, for each iteration in the for loop, is just going to be O of one space. Anyone confused about this? Ask now. A for loop here. So for each instance of the for loop, so let's say when I is equal to 0 and we go pay of sum 0, and then this here is going to be 0 plus 1, so that's 1. This only calls once for this iteration here. And once it finishes and it returns the results, it no longer needs to keep this function here in memory. So once we reach the end of the for loop here, it releases this memory for pay of sum accordingly. On the next iteration, it uses back the same memory location that you make, for lack of a better analogy, that was previously allocated to pay of sum. It just reallocates it back here accordingly as well. So it never adds more memory, it just keeps on reusing the same memory for each one of those function calls. And that's why it's only going to take O of one space here accordingly. The function here, because of the for loop, and we see it starts from 0 up to n, yes, there will be O of n calls to this pay sum function. But because this function here is not being called recursively, and each function call does not depend on another function call and so forth, it just keeps reusing the memory here accordingly. So that way it's just only going to be O of one space for each iteration here in the for. Whereas in our recursion, because we are dependent on the function being called by itself, that means that we need to allocate memory for each one of these functions here in order to get up to the final results for our recursion. The for loop here, we can use the same memory that's being allocated for pay sum for each iteration of the for loop itself. So we just use the same memory and we keep on reusing it together. So that's why it's going to be O of one space. And yes, it's because the recursive functions end up using the stack. Your iterative functions, because the function calls just basically reuse memory, it doesn't have to be on the stack accordingly. So in short terms, remember, because recursion keeps on calling itself, that means you have to allocate memory for each one of the function calls to recompute back up to your final answer. In iteration, this isn't the case. Each time when you call the function here inside the for loop, it just reuses the memory accordingly. Because once you hit the end of the for loop here, meaning this curly bracket, and you go out of scope of it, it just releases the memory accordingly until the next iteration. That same memory that was used from before is just reused again for your iterations. So that's why it only uses O of 1 here accordingly for regards to the space. So recursion uses more memory, iteration reuses the same memory. Right, so any further questions regarding this? O of 1 is better than O of n because we just now saw that in our analogy in the start. Because O of 1 is a constant, O of n is basically a straight line with a constant gradient. And yes, there are some cases where O of n is better than O of 1, but if they do happen to start at the same point, that's going to be the 0 point, O of 1 will always be better than O of n. And just to draw this out for you, what I mean by starting at the same point is if we actually physically drew this graph here, and this here is n and this here is t, n being the space, t is the time. O of 1 here will just be like that. But O of n here, if it starts at the same point here, will be like this. So we end up using more space regarding it and more time regarding it as well. Sorry, I said that wrong. We end up using more time regarding it in particular. Because this axis here is our O of n axis, not the n axis. Sorry. So yes, O of 1 is just basically a constant time, O of n is an increasing regardless. Alright, nice. Doesn't seem like there are any further questions, so go on ahead. So there are cases where the O of n code will run faster than the O of 1 code. And we saw that in our analogy at the start of our lecture, where the start point for O of n was less than the start point for O of 1. But this only happens for very specific inputs, and like I said, it's kind of rare for that actually to happen, because those are some extremely rare cases for the capture. The big O notation just basically describes the rate of increase with respect to time or respect to space. And if you do have some constants at runtime, let's say that was O of n plus 2 or O of 2 over 3 and whatnot, we just drop those constants because they don't add any value in describing the efficiency of our algorithms. So for instance, like if we had O of 2n, this 2 here doesn't really add much value. So because it's already linear in nature, we just say it's O of n, because we're just describing the rate of increase. We don't care how much it is increasing by or how much it is decreasing by. Once it is linear in nature, it's going to be O of n. If it's quadratic in nature, it'll be O of n squared. If it's cubic in nature, it'll be O of n cubed. If it's logarithmic in nature, it'll be O of log n, and so forth. We just care about the nature of it. We care about the specifics when we're using big O notation. Now, here's a teaser for you guys. Which one of these codes here is going to be faster? The code on the left or the code on the right? And I want to ask this question here. Apple. Let's see what you guys think. Right, let's give it a 30 seconds again and see if there are any last minute votes coming in. Alright, so voting has ended at this point, so let's wait for the results to pop up here in the chat. Looks like. So the majority of you thought that the left-hand side code here is going to be faster than the right-hand side. And when I guess the minorities here also thought that the right-hand side is going to be faster than the left-hand side. And then we have an extreme minority here who thought that it's neither. So the extreme minority here is right. Neither of these are faster than the other. And I'm going to explain to you guys why neither of these are faster than the other. They actually do take the same time. So this X here for our array on the left hand side, if our array here was size of n, that means that this loop that we see here is going to run n times for each one of those elements. The checks here are just going to be 1 and 1 here, basically to say, okay, it's checking these 1 for each one of these instances. And then if we multiply each one of these together, there's going to be O of n by 1, which is O of n. Alright, simple enough. This here is done n times as well, and this here is also done n times as well, right? This here is done once, this here is done once. So if this is done n times, and this here is also done n times as well, you may say, okay, that's O of n plus O of n. I'd be like, okay, that's 2 O of n. But no, this is where actually your analysis is actually going to be wrong. So let's restart this. I want to show you guys why it is wrong. So we know here that the loop here is going to run n times, right? So n times for this loop. But we're not going to be watching this. we're going to be watching what happens inside the loop. So this here, this check is going to run n times, and this check here is also going to run n times, right? That's n plus n equals to 2 of n. Similarly, when we watch on the right, these loops here run n times as well, but we don't care about those. We only actually care about what's going to be happening inside there, right? So this actually runs n here, and this runs n, but we need to add the two together, and that's going to be n plus n equals to 2n. And that's why neither of these codes here are faster than the other. They do take the same amount of time, regardless, because we are watching the instructions that actually do happen inside the loop. So even though that you do have a repetition of the loop twice, and each one of those has a single instruction, regardless if we had the loop and the instructions, we have two instructions inside the loop, it's going to take the same amount of time no matter what. And we saw the mistake at the start where we say, okay, the loop runs n times, and then each one of these runs once. So we say, okay, that's O of n, and then we saw that on the right-hand side, it's like O of n plus O of n. That's the wrong way to actually go about doing the analysis. You want to actually see what happens inside the loops here and how many times each one of these instructions are called with regards to. That's how we got 2 of n here, and then we got n here and n, and we add those two together, and we also got 2 of n. So they do end up taking the same amount of time, regardless of what happens. So remember this particular mistake, and it's common to make this mistake and not to make this mistake for any future analysis. That way you can get across this and know how to actually do the analysis properly. We also have to accept that in some cases, O of n being a linear time coefficient here is not always better than the O of n squared coefficient, which is going to be the quadratic relationship here. And the reason for this being is that once you go down to the number of instructions that we just did here, in some cases you will have to end up going down to the assembly level. And when you go down to the assembly level, which is like all the way down to machine code, multiplication operations in particular, when you go down to machine code, they do require a lot more instructions than addition. And your compiler hides this from you because it does a lot of optimization. So we don't really care about all this machine code. It's horrendously complicated, and we're not really going to be focusing on this. We're just going to be watching it at our C++ code level, and we're going to be using our analysis for our big O notation with regards to time and space complexity at this level only. We will not be going out to the machine code level. Things get very horrendously complicated. The one thing to note though is that multiplication operations, they do require a lot more instructions than adding two variables together. What about if we have expressions where we have n terms adding to each other, or maybe subtracting or some other sort of fashion, right? If it's going to be O of n squared plus n here, this plus n, it's not a constant, but it's also not very important, because the n squared here takes priority. So we just shorten down the order here to O of n squared, because this plus n, it already doesn't add much importance to the order or the behavior of the code. You also can drop other things as well, depending on which n term here takes superiority. So in O of n plus log of n, a linear relationship here takes precedence over a logarithmic relationship. So you just describe this as O of n. But this complicated equation here, we have 5 by 2 of n, 1000 n to the 100. This actually is just going to be O of 2 of n. And reason for this being is that n to 100, if n is 0 here, that's just going to be 0. If it's 1, it's just going to be 1, and so forth. This here will just end up being some sort of constant point, even though we have n to the power 100 here. The 2 of n here actually takes precedence for the entire equation, because this is going to be leading or superior order throughout the entire thing. Similarly, if you have two different variables where the variables do not have a relationship between each other, you will actually have to state out those variables for your order. So, for instance, if B and A here have no relationship between the two of them, you leave the order as is. So it's going to be of B squared plus A. That cannot be reduced. That's your final answer. And determining which terms are dominant, it's very simple. Just graph the terms. And whichever one tends towards infinity more than the other, it's going to be the more dominant one. So for instance, x of factorial here is the most dominant term for all of these, followed by 2 of x, x squared, x log of x, and then O of x. And then O log of x is the least dominant here, accordingly. There are horrendously worse runtimes than any one of these that you're seeing here on this graph. And I'm inviting you guys to actually go and look up for these horrendously worse runtimes. A good idea of something that you can look up, even though it's not very horrible, you may want to check up what's going to be the order for the square root of n. Because I did make a mention of that at the start of the lecture. That's something you might want to investigate. Alright, so that brings us to the end of our first lecture, and what we saw here is that with regards to describing the effectiveness of our algorithm or codes, we're going to be using the big O notation to describe the time and space complexity. We saw that for time complexity, this depends on how your code runs, whereas with space complexity, this depends on how much memory your code actually uses. We also saw that when we're doing the analysis for the complexities, and in our particular case, the time complexity, we go down to the instructions that are being executed to know how many times these instructions are being executed instead of looking at it from the loop level instead. Because the instructions is what actually is going to be played in the important part of how many times the program executes these instructions to determine which code is going to be faster or not faster, or both of them take the same time regardless. With space complexity, we saw that the difference between recursion and iteration, recursion uses more memory for each one of those function calls, whereas for iteration, it reuses the same memory, thus being more efficient regards to space complexity. We also saw that depending if you have multiple n terms in your order, you always choose the dominant or superior n term just to describe the space or time complexity of a particular algorithm or a particular piece of code. The other non-dominant terms don't really add much value because you're just describing the overall behavior of that code. If, for some instance, that you have multiple variables and there's no relationship between the variables, you are expected to state these variables in your order notations. So, for instance, where we had the fence, that's W meters wide and H meters high, that order is going to be order of WH. If we were adding P layers of paint, it's going to be order of WHP. Similarly, if we had an order of B squared plus A, and if there's no relationship between B and A, just leave the order as is because it cannot be reduced at any point in time regardless. Alright, so are there any final questions here at the end of our first lecture before I go on to our second lecture? You might want to explain what you mean by your accent if n can only be below 0. You mean like if it's going to be order of 1 or order of 0? Or do you mean n being the number of terms? this time complexity graph here on this slide. Alright, okay. So n here just basically describes the relationship of regarding how your order operates. So if your code expands linearly, we say O of n. If your code expands quadratically, we say O of n squared and so forth. It's just basically describing the relationship of how your code operates with respect to time and space. So let's say for your array, you have the size of it being n, and you have to go through each one of the elements in the array. That's going to be such that it's going to be that because you go through each one of the elements, that means you go through the array n times, so that's going to be O of n. N can take any value. So n doesn't have to be only 1 or 0. N actually can be any value. The only reason why we have O of 1, and we use that 1 there in particular, is just to describe a constant. So when we actually have O of 1 here, this here being O of 1, you can have like an O of 2, an O of 3 here, and so forth. But it doesn't really add much value when you say O of 2 and O of 3 and so forth. We just say O of 1 because we know that's going to be just a flat horizontal line with no gradient whatsoever. Because it's just going to be a constant value throughout the entire process no matter what. No matter how much n increases, it will always take the same amount of time no matter what. That's what we're seeing here. N can take any value, but if it's O of 1, it's not affected by n. If it's linear, that means that as n increases, t also increases by n. Meaning that the time for the algorithm operates accordingly with regards to as n increases. So that's why we get that linear relationship. It's like saying if you have to sort n items, and let's say if it was just only one item, you take 1 second to sort this. But if it's 2 items, you're going to take 2 seconds. 3 items, it takes 3 seconds. 4 items, it takes 4 seconds, and so forth. You get that linear relationship by getting that description because we know that the gradient here is going to be 1. And when you go up to n items, it takes n seconds. So that's how we get O of n. So it's just a nice way to describe the relationship of how long your algorithm will take with respect to the amount of items you're dealing with in the code. So for instance, we had O of 2 of x here. Well, I would say x here was just basically n. As the number of items increase, being n being the number of items, the time it takes is going to be 2x time in order to go about doing its operation. So let's say if you had 1 item, it's going to take 2 seconds here. If you had 2 items, that would be 2 to the power of 2. It's going to take 4 seconds. 3 items, it's going to be 2 to the power of 3, so it ends up taking 8 seconds and so on. So the order here just basically, or the O notations, describes that relationship between the number of items versus the time it's going to take. Similarly for x squared, well, like I said, if x was n, if we had 1 item, it's just going to take 1 second because that's 1 squared. If we had 2 items, it's going to be 2 squared, which is 4 seconds. If we have 3 items, it will be 3 squared, which it takes 9 seconds. And so that's how the relationship operates in regards to it. So it can typically be like saying, yeah, y-axis here is time taken. And your x-axis here is number of items. The time taken here is going to be O of n, and the number of items here is n. In this case, because it's with respect to x, it's going to be O of x, and this here will just be x. Right. Any further questions? Alright, doesn't look like we have any further questions, so let's move on to our second lecture for today. Taking annotations.